Lab 3 focuses on experimentally analyzing the magnetic field of a bar magnet in both the axial and perpendicular positions. The magnetometer app used in this experiment was Physics Toolbox. The phone with the app open was aligned with Earth's north-south magnetic axis and was then repositioned across a ruler to determine the magnetometer sensor. The goal of this experiment was to use the measurements of distance and magnetic field to determine the magnetic dipole moment mu, and also to observe the inverse relationship between distance and magnetic field. Figure 1 shows the example setup for measuring the distance and B field on the axial position. The red X marks the magnetometer sensor. This experiment mainly observes these fundamental principles and concepts: the Biot-Savart law for determining magnetic field, the concept of a bar magnet as a dipole, the distance-dependence relationship given in the lab instructions, and finally, that the Earth has a constant magnetic field. The magnetic dipole moment was determined to be 3.83 amperes times meters squared, and of the statements on the right-hand side, the above two were observed. When the magnetometer is far away from the magnet, it measures a near-zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. The left-hand figure shows the axial measurements of distance and their respective magnetic fields in the x component. Figure 3 displays the averages of the previously collected data with distance in the left column and the magnitudes of the x component of the magnetic field on the right. Finally, Figure 4 displays the distances and the magnetic field components of the perpendicular dipole measurements. By corrected subtracts By Earth from By measured because of Earth's contribution to the magnetic field measured in app with its own magnetic field. To calculate the magnetic dipole moment of the bar magnet, both the distance dependence formula given in the lab and the Biot-Savart law for a magnetic dipole formula were used. To quantify the variables in the distance dependence relationship, a plot was derived from the logarithmic form of the distance dependence equation. Here, both the experimental constant k and exponent n could be determined. The log of k was represented by the y-intercept of the linearized equation, and n was the slope of the graph. With n and k determined by the graph and r distance to be referred to in the measurements, both equations could be set equal to each other to determine magnetic dipole moment mu. Figure 8 shows the derivation for calculating magnetic dipole moment mu and was applied 5 times to calculate the mu using each distance average. The average of the 5 moments was then taken to get an average magnetic dipole moment of 3.83 amperes times meters squared. The following figure displays a model of the experimental system including observation points for the axial and off-axis positions, as well as an intermediate location at 45 degrees. The orange arrows represent the on-axis magnetic field arrows. The cyan arrows represents the off-axis magnetic field arrows. And finally, the magenta arrow represents the magnetic field arrow at an observation location 45 degrees from the axis. The rectangular silver magnet is located at the origin. The VPython code includes 3 main parts: creating the magnet at the origin, creating a function for magnetic field, then utilizing this function to find the magnetic fields at these different observation points. The code at the bottom creates an arrow for the axial position and is similarly structured for the remaining observation points. Now, what if the experiment wasn't correctly oriented to compensate for Earth's magnetic north? If the phone were instead laid out at some intermediate angle, the magnetic field measurements in the app would include the additional influence from Earth's magnetic field, and the magnet would have a greater magnetic field than normal. Furthermore, the y-intercept or the log of k would actually be less negative, consequently affecting the magnetic dipole calculations. And what if, instead of one magnet, there were 2 lying end to end? This would double the magnetic field due to the superposition rule. With each magnet exerting the same magnetic field at the same observation point in the same direction, both fields would be summated according to the superposition principle, thus doubling the original magnetic field.